Introduction to Stimulation. Hello, welcome to this presentation. I coupled this presentation together from various sources, which I will not cite because that will take me a few extra seconds, and it doesn't particularly matter. Made this mostly because I'm bored. I'm going to read through it rather poorly, just so you can have a voice narrating the slides. It'll primarily be a matter of reading text on the slides, so you can do that yourself if you don't want to listen to me. Stimulation is a treatment performed to restore or enhance the productivity of a well. Stimulation treatments fall into two main groups. Hydraulic fracturing treatments are performed above the fracture pressure of the reservoir formation and create a highly conductive flow path between the reservoir and the wellbore. Matrix stimulation is designed to treat the near wellbore reservoir formation rather than other areas of the production conduit, such as the casing across the production interval, production tubulars, or the perforations. Other groups of stimulation treatments include sand control, which prevents migration of reservoir sand into the wellbore or near wellbore area, water control, which is conducted within a reservoir or perforated interval to reduce water production, and wellbore cleanup. We stimulate wells to increase production. It's a lucrative practice. Recent concerns in well stimulation include horizontal drilling, scarcity of resources, depressed gas prices, and increased environmental awareness. Critical parameters for stimulation include what type of well? Is it oil or gas? What will the cost be? How will you be able to distribute proppant in a complex fracture? Conventional reservoirs. A conventional reservoir is a reservoir in which buoyant forces keep hydrocarbons in place below a sealing caprock. Reservoir and fluid characteristics of conventional reservoirs typically permit oil or natural gas to flow readily into the wellbores. Excuse me for that. The term is used to make a distinction from shale and other unconventional reservoirs, in which gas might be distributed throughout the reservoir at the basin scale, and in which buoyant forces or the influence of water column on the location of hydrocarbons within the reservoir are not significant. Conventionals are stimulated to connect with the natural fracture system, especially gas shales, to increase the effective drainage area, to produce complex reservoirs, example being discontinuous sandbars, to increase wellbore stability, that is to say to minimize drawdown, to increase production efficiency or flow capacity, overcome formation damage, or enhance production from low permeability wells. Unconventional resources are oil and natural gas that is produced by means that do not meet the criteria for conventional production. At present, the term is used in reference to oil and gas resources whose porosity, permeability, fluid trapping mechanism, or other characteristics differ from conventional sandstone and carbonate reservoirs. Examples include coalbed methane, gas hydrates, shale gas, fractured reservoirs, and tight gas sands. Hydraulic fracturing is a stimulation treatment routinely performed on oil and gas wells in low permeability reservoirs. Especially engineered fluids are pumped at high pressure and rate into the reservoir interval to be treated, causing a vertical fracture to open. The wings of the fracture extend away from the wellbore in opposing directions according to the natural stresses within the formation. There are two kinds of fracturing. There's propped fracturing, in which proppant, such as grains of sand of a particular size, is mixed with the treatment fluid to keep the fracture open when the treatment is complete. There is acid fracturing, in which acid, usually hydrochloric acid, is injected into a carbonate formation at a pressure above the formation fracturing pressure. Variables that are controlled when designing a fracture treatment include fracture width, which is between about 1/10 and 1/4 of an inch, proppant concentration, proppant pack permeability, which varies from 0 to 300,000 millidarcies, closure pressure, size of the proppant, type of proppant, the damage imposed by the treatment fluid, and the fracture length can be between 25 and 1,500 feet. There are two major kinds of propped fracturing treatment. Gel fracturing fluid, and there's slickwater. In slickwater, non-viscous fluids pumped at high rates, above 60 barrels per minute, generate narrow fractures with low concentrations of proppant. These treatments have become a standard technique in fracture stimulation of several U.S. shales, including the Barnett, Marcellus, and Haynesville. The most critical chemical additive for slickwater fracturing execution is the friction reducer. The video to the right is a demonstration of what slickwater fracturing looks like in a lab setting. Slickwater and Gas Shale. Gas shale is shale that produces natural gas. A shale that is thermally mature enough and has sufficient gas content to produce economic quantities of natural gas. It will have ultra-low permeability, heterogeneous mineralogy, and benefits best from slickwater or uncross-linked fracturing fluids. Advantages of slickwater include that it is easier to corner in complex fractures, has longer hydraulic half-lengths, has a high retained conductivity due to no filter cake being present, has reduced sensitivity to salinity and contaminants in mixed water, it has reduced number of fracturing fluid additives required for the slickwater. Disadvantages of slickwater include low height coverage due to settling of the sand, low proppant concentrations, high water use, larger horsepower requirements to obtain high pump rates of 60 to 110 barrels per minute. It's a limited fracture width due to low maximum concentration of proppant in a low viscosity fluid. It has reduced percent flowback water recovery due to imbibement of fracturing fluid in complex fracture network far from the wellbore. It's limited to fine mesh propping agents due to reduced ability of non-viscous fluids in transport of large proppants. Gelled fracturing fluids. Basic components of a gel fracturing fluid include the base fluid, which is usually water, but sometimes a hydrocarbon, but most often diesel oil, a thickener, most often a polysaccharide, example being guar and derivatives thereof, cellulose and its derivatives are often used, xanthan is another one, xanthan, viscoelastic surfactants, and some synthetic polymers. In addition, cross-linkers are used to increase the viscosity of the fluid, in addition to the gelling agent. Advantages of gelled fracture fluid include better height coverage, higher proppant concentrations, and higher fracture conductivity than slickwater or uncross-linked fluids. Disadvantages include that the gel damages the proppant pack. The video you see here is a lab setting example of what a gelled proppant fracturing treatment will look like. Now, these images show a polymer chain, guar polymer chain, and a borate crosslinker, very commonly used borate crosslinker. See, boric acid in a high pH environment will become the borate ion, which will enable crosslinking. You see in the graph to the right, borate ion only appears appreciably after about pH 8. It starts disappearing after pH 12, which is why we say that borate crosslinkers are useful in a pH range of 8 to 12. Here we see an illustration of borate ions forming hydrogen bonds between adjacent guar polymers, thereby effectively increasing the molecular weight of the polymer. Wellbore cleanup. In wellbore cleanup, fluids are injected into the wellbore, but not into the formation. These treatments include production chemical treatment, Perforation washes. These treatments and washes are used to remove mud, paraffin, and other restrictive damage from the wellbore near the perforations to ensure optimum production from the reservoir. Sand control. In weak formations, sand control may be necessary to maintain the structure of the reservoir around the wellbore. In other formation types, the migration of sand and fines into the near wellbore area may severely restrict production. Sand production in excessive amounts can cause sand bridging in the tubulars, casing or lining failure, erosion of equipment, and high sand disposal cost. The principal sand control techniques include gravel packing and sand consolidation. These techniques include resin-coated gravel, screens, slotted liners, or pre-packed screens. Hydraulic pressures during placement of these materials must be carefully calculated to avoid accidentally fracturing. Water control. Water control treatments are designed to eliminate excessive water production that does not help produce oil and depletes the reservoir pressure. Water control treatments may be necessary when the production efficiency of a well or the process capability of surface facilities is compromised by the volume of water produced with the oil or gas. Treatment options include selective isolation of the water-producing perforations, localized treatment of the formation matrix. These treatments can be polymer-based, inorganic gel, resin-based, cement-based, polymer injection, or they can be mechanical. Matrix treatment. Matrix stimulation is a process of injecting a fluid into the formation, either an acid or solvent, at pressures below the fracturing pressure to improve the production or injection flow capacity of a well. This improves the permeability of the near wellbore formation, enhancing the productivity of a well. The goal of a matrix treatment is different in sandstones than in carbonates. In sandstones, matrix treatments restore or improve the natural formation permeability around the wellbore by removing formation damage, by dissolving material plugging the pores, or by enlarging the pore spaces. In carbonates, matrix stimulation creates new, highly conductive channels, called wormholes, that bypass damage. The selection criteria for the treating fluid are also distinct. For sandstone treatments, knowledge of the extent, type of damage, location, origin, reservoir mineralogy, that would be a petrographic study, and compatibility of the treating fluid within the formation are especially important. In carbonate treatments, reservoir temperature, pumping rate, and fluid type become more significant because these parameters directly affect the reactivity of the treating fluid with the reservoir rock. Sandstone treatment is generally composed of hydrochloric acid pre-flush, a main treating fluid, a hydrochloric acid mixture, an overflush, a weak acid solution or brine. Organic acids such as formic and acetic acid are used in either sandstone or carbonate acidizing, mainly in retarded acid systems or in high temperature applications. Flow reduction. Flow reduction through the wellbore can be reduced by scale damage, by sand fill, by plugged perforations, by paraffin plugging, and by asphaltene deposits. Coiled tubing is often used to run perforation washes or chemical treatments to fix these problems. Coiled tubing is used because of its smaller pipe diameter, which reduces the amount of fluid needed to complete the task. Flow through the critical matrix can be reduced by drilling mud, cement, completion fluids, production, or native fines and clays. Here you see an illustration of the critical matrix. The area within 3 to 5 feet from the wellbore into the formation is called the critical matrix. A near wellbore area where injected fluids such as acids can restore original permeability. Most of the reservoir pressure drop during production occurs in this near wellbore part of the reservoir. While there is an almost negligible pressure drop from a given radius to a 10-foot drainage radius, there is a huge pressure drop from a 5-foot drainage radius to a 0 drainage radius. Matrix acidizing. Well completion almost invariably results in damage to the formation, especially within the critical matrix. A matrix treatment is designed to restore the natural permeability of a formation by treating the critical matrix. By using acid as a minor stimulation in the critical matrix, pathways are etched in the formation. These pathways increase the permeability of the critical matrix while leaving the zonal barriers between production fluids and unwanted water or gas intact. Matrix treatment is employed to reduce the pressure drop between the reservoir pressure and the wellbore pressure. This treatment is recommended for high permeability formations with damage, for unprobable formations, for thick zones, to supplement a fracturing treatment, and when damaged or weak tubing disqualify a well as a candidate for fracturing. To the right, you see an image of a wormhole. In sandstones, fluid and fines invasion into the formation during completion operations is often the cause of reduced permeability in sandstone formations. A matrix treatment is designed to dissolve or disperse these particles while avoiding any effect on the natural sand in the formation. This results in restored permeability and the sometimes minor stimulation of the reservoir. In a limestone formation, the acid treatment enlarges the flow channel fractures within the rock. It disperses damage by dissolving the surrounding rock, and creates highly conductive wormholes to increase flow into the wellbore. Skin. Skin is the zone of reduced or enhanced permeability around the wellbore, often explained by formation damage and mud filtrate invasion during drilling or perforating, or by well stimulation. An infinitely thin zone that causes a steady-state pressure drop at the sand or formation face. Skin is a dimensionless factor calculated to determine the production efficiency of a well by comparing actual conditions with theoretical or ideal conditions. Positive skin values indicate some damage or influences that are impairing well productivity. A negative skin value indicates enhanced productivity, typically resulting from stimulation. There are a couple kinds of skin. Total skin. When determining the flow capacity of a well, it is necessary to account for the total skin acting on the well. The total skin is the sum of the formation damage and all pseudoskins. Pseudoskin. In addition to skin, other pressure differentials, such as those caused by fractures, turbulence, fissures, and hardware restrictions, are considered to be pseudoskin. Pseudoskin can be created when a well produces at a high rate. Some causes of pseudoskin are turbulence or collapsed tubing, partial penetration, partial perforations or plugged perforations, downhole pumps, downhole valves, chokes, and completion in general. If the skin is zero, the well is neither stimulated nor damaged and is considered a naturally flowing formation. In a damaged formation, the skin is greater than zero. In a severely damaged well, total skin may be as high as 200. In a stimulated formation, the skin is less than zero. In a stimulated well, -4 is as good as almost any well will perform. Mechanical skin is the only type that can be removed by stimulation, although other factors, for example tubing size, can greatly affect the flow rate from a producing well. Formation damage. During completion and production, a formation may be damaged in a number of ways. By scale formation, by organic deposits, by silt and clay, by emulsions, by water block, by wettability changes, by bacterial slime. Each type of damage has a recommended treatment. Scale formation. Scale is a deposit or coating formed on the surface of metal, rock, or other material. Scale is caused by precipitation due to a chemical reaction with the surface, precipitation caused by chemical reactions, a change in pressure or temperature, or a change in the composition of a solution, such as when incompatible mixed waters come together. Scale deposition from brines can occur whenever the mineral saturation exceeds the critical equilibrium saturation. The term scale is also applied to a corrosion product. To the left, you'll see an image of scale forming on the inside of a tubular. Scale damage usually results in a sharp drop in production. If scale is damaging to the formation, scale will be visible on the pump jack rods or on the tubing when it is stripped out of the wellbore. Scales typically occur in the wellbore. For this reason, wellbore cleanup treatments rather than matrix treatments are used for this type of damage. Typical scales are calcium carbonate, calcium sulfate, barium sulfate, strontium sulfate, iron sulfide, iron oxides, and iron carbonate, though there are others. Carbonate scales are typically treated with hydrochloric acid. Barium sulfate scales are typically treated with EDTA. Organic deposits. It's a type of damage in which heavy hydrocarbons precipitate when temperature or pressure is reduced. The injection of cold treatment fluids promotes the formation of organic deposits. These deposits are commonly located in the tubing, gravel pack, and perforations, or inside the formation. Organic deposits such as paraffins or asphaltenes are resolubilized using aromatic organic solvents such as toluene or xylene, or mutual solvents such as 2-butoxyethanol. Small amounts of alcohol or other polar solvents help to further dissolve asphaltenes. Operators often prefer a hot oiling method because of its lower costs. Paraffin is usually visible on rods and downhole pumps if deposits are accumulating. To the right, you'll see a simple guide to figuring out whether an organic deposit is paraffin or asphaltene. Silts and clays. Silt is a particle whose size is between 2 and 74 micrometers, or 200 mesh. Clay can refer to fine-grained sediments less than 0.0039 millimeters in size. Clay is also a group of rock-forming, hydrous aluminum silicate minerals that are platy in structure and can form by the alteration of silicate minerals like feldspar and amphibole. Common examples include chlorite, illite, kaolinite, montmorillonite, and smectite. Clays are mined from surface pits as relatively pure deposits and used for bricks, pottery, foundry molds, and in drilling fluids, among other uses. Clays, as claystones, shales, and intermixed with sands and sandstones, make up the largest percentage of minerals drilled while exploring for oil and gas. Some clays, such as montmorillonite, have the tendency to swell when exposed to water, creating a potential drilling hazard when clay-bearing rock formations are exposed to water-based fluids during drilling, possibly reducing the permeability of a good reservoir rock. Crystal structures are determined by X-ray diffraction. These structural differences determine the amount of surface area exposed to the reservoir fluids. Damage from silts and clays include the invasion of the reservoir permeability by drilling mud and the swelling and/or migration of reservoir fines. Migrating fines can bridge pore throats and restrict fluid movement, causing formation damage. Damage from silts and clays results in a sharp drop in production. Production and ARC tests can be run to determine if silts and clays have damaged the formation. Clay stabilizers are the recommended treatment for silts and clays. Include quaternary amine polymers, cationic surfactants, hydrofluoric acid for sandstone. In carbonate reservoirs, hydrochloric acid may be used. Hydrofluoric acid for sandstones. Emulsions. An emulsion is a dispersion of droplets of one liquid in another liquid with which it is incompletely miscible. Emulsions can form when fluid penetrates or injected fluid Emulsions can form when fluid filtrates or injected fluids and reservoir fluids, for example oil or brine, mix, or when the pH of the producing fluid changes, such as after an acidizing treatment. However, some natural and artificial stabilizing agents, such as surfactants and small particle solids, keep fluids emulsified. Among the most common solids that stabilize emulsions are iron sulfide, paraffin, sand, silt, clay, asphaltene, scale, and corrosion products. Emulsions can form in heavy oils that contain a significant amount of asphaltenes. The asphaltenes act as surfactants with treatment or formation water. The resulting emulsion droplets have high energy bonds, creating a very tight dispersion of droplets that is not easily separated. These surface-acting forces can create both oil and water and/or water and oil emulsions. Such emulsions require temperature and chemical treating in surface equipment in order to separate. Emulsions are typically treated using mutual solvents, again such as 2-butoxyethanol. Water block. A production impairment that can occur when the formation matrix in the near wellbore area becomes water saturated, thereby decreasing the relative permeability to hydrocarbons. Water block may result from the invasion of water-based drilling or completion fluids, or from fingering or coning of formation waters. The increased presence of water causes fine clay crystals that may be present in the formation, such as illite, to swell and cause a reduction in permeability. Water block treatments typically use mutual solvents and/or surfactants to reduce the surface tension between the oil and water, helping to displace the water from the near wellbore area. The most extreme cases of water block occur in low-pressure, low-permeability gas formations, where alcoholic acid systems are recommended because they promote water vaporization in the produced gas. The acids normally employed are usually either hydrofluoric acid, hydrofluoric acid mix, or hydrofluoric organic acid mix, wherein the organic acid is formic or acetic. The alcohol is either methyl or isopropyl. Wettability changes. Wettability change is a type of damage in which the formation wettability is modified, generating a change in relative permeability that affects well productivity. Surfactants or other additives in drilling fluids, especially oil-based mud or other injected fluids, can change formation wettability. Wettability is characterized by a rapid production decline. The wettability change may be a result of a casing leak, water breakthrough, water coning, or a decrease or disappearance of gas. A naturally water-wet formation could be changed into an oil-wet formation with consequent production impairment caused by reduction of oil relative permeability. Wettability change is normally treated with mutual solvents to remove the rock oil coating, asphaltene or paraffin precipitation, followed by a strong water-wet surfactant to reduce the tendency of further hydrocarbon precipitation. In the image to the right, you'll see some illustrations of oil-wet versus water-wet formation. On the left, you see a water-wet formation, in which water is clinging to the faces of the formation grains, the particles, and in the pore spaces, oil may flow freely. On the right, you'll see the opposite, in which oil is clinging to the formation particles, and it is the water which is flowing freely. Bacterial slime. Slime-forming bacteria can live with or without oxygen and produce mats of high-density slime that cover surfaces. Anaerobic bacteria can grow downhole without oxygen in temperatures lower than 150 degrees Fahrenheit. Their primary detrimental effects are the production of sulfate-reducing bacteria and pore plugging. Sulfate-reducing bacteria react chemically with sulfates in the formation to create hydrogen sulfide. This problem is normally treated with bleach, sodium hypochlorite. This image summarizes the areas where certain damages occur. Scales, organic deposits, and bacteria can appear in tubing. Scales, organic deposits, silts, emulsions, bacteria can appear in the gravel pack. Scales, organic deposits, silts and clays, emulsions, bacteria can appear in perforations, and they can all appear in formation.